my goal today is to do a little bit more time. I wish I had a week to do chain roll. There's so many flavors of it, so many different ways, different situations that you can use it. But we just don't have the time. So here goes. I've actually written them down to try and keep me on the straight and narrow. Here are some versions of homework questions. I picked them because they're a kind of little flavour of all sorts of different situations. And I'll probably do one of these, how to find the equation of a tangent line as well. And that's pretty much all we can do on the chain rule. They're going to be, I guarantee, a situation that I've not covered because there's an infinite number of them. So you got to just basically identify the inside function. That's the key to doing all of these. So before I even look at these questions, if I was doing this one, would you agree that's the inside function? Right. If I'm doing this one, that's the inside function. If I'm doing this one, the t cubed is inside function. Now in this question here, it's clearly a product rule, right? So there's two things being multiplied. So this guy here is the inside function for the f, and this guy here is the inside function for the g. And if you're doing this one, again, it's a product rule, but that's the inside function, and that guy there is doesn't need an inside function, right? It's just start at the half. So identifying that's a good way to start a question you've never seen before. And then from there, you just say, differentiate the function times the derivative of the inside function. And that at least gets you along the road. So, first one. I'm going to call it r to the half, e to the power of r to the 6 add 4. And when I have a situation that is a little bit complicated, as we have here, because this is a product rule, I like to do part of the working at the side, which you've seen me do yesterday. So if you want the derivative, it's f dash g plus f of g dashed. So r to the half, because I just turned the square root into that, differentiate it, multiply by the power, reduce the power by 1, call that done. Function g, oops, 4 goes there. There's your inside function. So you want its derivative, it's e to the power of that guy times the derivative of the inside function, which is that guy. Probably do the next line here. So f dashed is this guy, g is that guy, f is that guy, g dashed is that guy. Now, when you do a product rule, you're going to have two terms separated by a plus. We're finished with the calculus. What very often is more difficult is the making it look pretty, right? My style point thing. And most of that time isn't it going to be picking common factors, if there are any. Now, if there's no common factors, your life just got easy, you're finished, right? But the chances are there probably going to be some. And some common factors are obvious, and some common factors are very weird. Would you be agreeing that the r squared plus 4 is a common factor? Right. So I'm going to definitely pull that out. That was an easy one to identify. Even though it looked ugly, it was easy to identify. Now it gets a bit messier. There is an r to the negative a half, and there is an r to the half and an r to the 5 halves, which is, if I had time, I would put them together and call them 11 halves. So rather than rewrite an entire line, can we just combine those two and say 5.5 is r to the 11 halves, okay? We're okay with that, okay. So negative a half and 11 halves. There's a common factor there. It's a power of R. And the rule is the smaller of the two. Right, that's always the ugly one. Right, common factor's finished. Let's see what we get. That guy used up. That guy used up. Only thing left over, a half. These two guys are him. So you've 11.5 powers, take away a negative a half. Well, isn't that adding a half? 11.5 plus a half, 12 halves, which is 6. So you're going to get an R to the 6. Used up and a 6 left over. So I guess my bracket's finished there. And then make it look like the original. Well, the only guy that's really not quite fitting is that negative of power, right? Would you agree that doesn't match the start? And we've done a few of these now. Negatives become positives on the bottom, and that's better, but not perfect. There, we are done. So you're going to be doing a fair amount of algebra in quite a few of these. Not all of them, but in quite a few of them. Are you okay with that one? I've seen ones very similar, I think, yesterday. Right, let's move on to my second one. This is similar to 14. Okay.
Ready.
Right, let's see what's going on here. Right. Definitely a product draw. That's the F, that's the G. So I know when I'm going to find its derivative, it's going to be F dash G plus F of G dashed. And I'll take these guys over here because I didn't have enough room to squeeze it in there. We have 4x plus 3 cubed. And now its derivative. Don't know why I went right there. That's your inside function. So it's going to be 3 times this guy squared, followed by the derivative of the inside function, which is 4. And I'll tidy that up to get that. There's F done. Now G is this guy. This one's not that bad, actually. It's just long. Right, there's your inside function, this piece. So it's 4 lots of that guy to power of 3 times the derivative of the inside function. Well, if you differentiate this guy, you get that. And that's G. Now we can continue. F dashed. 12 lots of this fella times the untouched G. Plus, leave the F alone. And this guy. Yikes, even with that room, I didn't leave myself enough room. Okay, so it's going to be 4 lots of x squared, take away 5x, add 3 times a 2x minus 5. Now that was close. Okay, time for style points. You are looking at 2, right, expressions. And you're going to look at this one, and then you're going to look at this one, and you're going to pick out common factors. Well, that guy's got a 4, and that guy's got a 12. So I'm pretty sure 4 is a common factor. I got a 4x plus 3 squared and a 4x plus 3 cubed. So when you have a choice, you always pick the smaller pair. I have this guy to the 4. I have this guy to the 3. So I'm going to pick this guy to the 3. Are you comfortable about the choice of common factors? The 4, that guy squared, that guy cubed, right? Each one has it, choose the smaller pair. And then you just kind of go in and you see what's left over. Well, 4 into that leaves me with 3. That one was used up and one of these is left over. Plus, used up, one of these left over, used up, 2x take away 5. Now, I'm not quite finished, but I'm going to save some time here. What do you think I should do next? That's not finished. What do you think I should do next?
Simplify what's in the brackets.
Yeah, just FOIL, distribute that, collect like terms. There's going to be some ugly quadratic left over, but that's the end of it, right? And it wasn't anything really spectacular going on, I guess, just time consuming.
So what I'm not too clear on is the first step. So you got 12 times 4x plus 3 to the second. How do you get to 12 again?
Where did that 12 come from? Let's see. This was the original function. We're now about to differentiate it. So you multiply by the power 3, this guy squared, times the derivative of the inside function. So if you differentiate this guy, you get 4. And the 3 and the 4 combined, and that's where the 12 came from.
Okay, all right.
So the trick here is to keep your eye on the inside function when you're doing the general. Now, 18 is actually not going to take us too long.
So what is the chain rule used for?
The chain rule is used for differentiating functions that are essentially compositions of functions, right? Complicated interactions, you know, like a weird power like this, or a product rule where the E was a weird power, or I haven't got any right now, but you know, things like the sine of t squared plus 4, that would be a chain rule situation, right? We know how to differentiate the sine of t, but we don't know how to differentiate the sine of a function of t, like the sine of t cubed, or the sine of t squared plus 1, or even the sine of the cosine of t, which is weird, but you can do that as well. So the chain rule is going to be used to find derivatives of any function that is basically a composition of 2 or more functions, right? A combination of things that aren't simply just x's or t's. The minute you've got a t squared or an x cubed or a sine x where there shouldn't be one, that's probably going to be a general. Right. Now this guy, if I asked you to do the derivative of 6 to the power of t, isn't its derivative that guy? Because we told you it was. Remember, it's one of the ones that you got. Now, in this question here, 6 to the power of t cubed, the t cubed is what we call the inside function. So when we differentiate it, we will get the natural log e6, 6 to the power of t cubed. You know, very similar to what you get if it was just t, followed by times the derivative of the inside function, which is 3t squared. And all I'm doing here is rearranging the furniture from simplest to ugliest. And we're done, right? So there's really not a lot of style points in that one. Now, if you move on to something like 21, And let me rewrite that again. For some reason, I picked up an extra t. There we go. Can you see that this one is definitely a chain rule, right? E to a really weird function, right? Not only that, do you notice something about the inside function?
Is there supposed to be a 6 before the t?
I have no idea. It's meant to be a 6 before the t. There we go. If you're looking at the inside function, God, am I writing today? This is just for my benefit. You don't need to rewrite this again. My 6's do look very like t's, don't they? I'm trying to make them less, similar, right? So that's
Six
the
T,
same.
Professor. You have
Say
six
again?
sign, and you have 6 sign instead of 6 T sign.
6 and a t.
Oh. Let's try the 4th time. That's even more interesting. That's what probably I thought the first time. Right. Same question. The inside function is a problem. So I'm going to start by doing the easy bit. The derivative of e to any ugly power is e to that same ugly power, followed by the derivative of the inside function. And I don't normally write this line down, but I am today. Have you noticed that I'm going to use a product rule to find the derivative of the inside function? So at the side, I now have to figure out how to do the derivative of that guy. And that is f, and that is g. It would have been much easier, wouldn't it, if that had just been 6, because it would have not needed to be a product rule. But it is, so we'll live with it. So it's going to be f dash g plus f of g dash. Now, starting here and everything that's about to follow is only so I can find out what the derivative of this is. Once I get the answer, this just gets replaced by it. It's probably going to be messy, but that's what it is. Now, the first function is 6t, nothing really too horrible. Its derivative is 6. The second function is the sine of 2t, and now I'm going to do a deliberate mistake. Oh, sine of 2t is the cosine of 2t. What is the mistake? What should the answer to g dashed really be?
Sine 2T should be the double angle identity to sine
Oh,
T
don't
cosine
need to
T.
go there, Robert. I know what you're thinking. And eventually you would get the right answer, but that's a long way to do it. It's a little bit quicker. So think simple rather than making life hard for yourself. So the derivative of sine 2t is the cosine of 2t. That's not my mistake. My mistake is I've missed something.
Shouldn't you have the 2 in front of the cosine?
Yes, because isn't it a little baby chain rule?
Yeah, because
That's
you
what
got
I
to
was-
take the derivative of the inside, right?
Yeah. Right. So I should have made that question clearer, right? That's what I was getting at. I missed it too. So put all the pieces together and you get 6 times the sine of 2t plus 6t times this guy. And then just a little bit of tidying up here. 6 times the sine of 2t plus 12t, the cosine of 2t. And we now can put the package together. And we have this guy. And the derivative, which is all of this. I can do a minor piece of cosmetics, but nonetheless we're expected and should do it. Is there anything I can do style points to this piece here? Can you see anything here that we could do that would make it a little bit nicer looking?
Oh, you can take out the 6.
That's the one. Now, that brings me to this kind of side issue. WebAssign is not consistent with style points or what it would do. It wouldn't surprise me at all if WebAssign was happy with that answer. But just because WebAssign is happy with it doesn't make it right. Okay, so be careful when you're doing your answers. It may well be correct as far as homework and WebAssign is correct, or it says it is, but that doesn't mean that it is 100% correct. So always look at your expression and say, is there any common factor I could do and pull out of this? Is hopefully not too often, is there a trig identity that I could use? Right. Someone was talking about a question where one of the answers ended up looking like that. And actually, I'm pretty sure if you typed that into WebAssign, it would say it was correct. But that's actually the correct answer as far as style points go. So just be aware that WebAssign might accept your answer, but that doesn't mean that it's the best version of that answer that you could. Okay, last one of this, and then I'll probably pick one of these rather than both. I want to differentiate this guy. First thing I'm going to identify is the inside function. In fact, if you ever see brackets, isn't it 99 times out of 100, isn't the thing inside the brackets an inside function, right? You can kind of see that. Now, in this case then, we're going to do 3 times this guy, the inside function, squared, times the derivative of the inside function. Now, if you want to differentiate, put it up here. If you want to differentiate cos squared z, you got to realize that it's actually that guy. And so it's really a chain rule. So differentiate 6, you get nothing, right? Differentiate the cos squared. I have to think of it like this. So that makes it 2 times the cosine of z to the power of 1, so nobody writes that, followed by the derivative of a cosine, which is in turn negative sine. And here style points with trig kicks in. Let me just ignore that expression for a minute. If you multiply these together, don't you get negative 2 sine z cosine z? Do you see it's this guy? So all of this, 2 times cosine times negative sine z, turns into that, and that guy is him, right? This is a trig identity called the double angle. So what I've now got is just a negative, that guy there, 3 times the sine of 2t, 6 plus cos squared z squared. Now, could WebAssign accept what you might have thought the answer should have looked like? Sometimes yes, sometimes no. It's pretty inconsistent about what it would take. But this guy is him. But this is considered better, right? Simply.
So you said that the one is a trig identity. Which identity is it?
It's called a double angle identity. So have I got those? Doing them earlier. Right. Here's some examples of the double angle identity. The one I just used was a version of this one, which is reasonably common. It's probably the most likely one you see, but there are others.
Okay, I think I saw one of the notes in one of the sections that there's a section in the back that has the trig identities. I'll go and check those out again. It's been a while.
It's been a while for quite a few people, so you're not the only one. I'm just writing down all the double angle ones that you get. There's only one double angle version that gives you the sine E2t, but there's 3 flavors of the double angle identity that give you the cosine E2t. So you might, well, I can imagine it happen. Can you imagine you differentiated something and this was part of your answer? Then you turn it into a cosine E2t. And these are pretty rare, but I guess it could happen, right? You would turn them into cosine t's.
Professor,
Oh, yes.
Oh,
sorry to interrupt. That
Mhm.
cosine squared t minus sine squared t, if
Mhm.
that to sine squared t minus cosine square t,
Yeah.
is that still the same thing? Can we still
No,
use
it's
that?
negative the cosine E2t then.
Okay.
If they switch places. If any of these 3 switch places, right, that goes there and this goes there, then you need a negative. A bit like a minus b is the negative of b minus a. It's that kind of identity.
I think there's actually a homework problem that has that, but I didn't put it in, so I need to
Okay,
go through
so
my notes.
you can go and check it out.
is that where in the question 24? I'm guessing you just replaced the T with Z.
Yeah. The T and the Z. Yeah, that's all I did.
Okay. Okay.
I mean, you could replace it with X because the variable here doesn't change the identity. Right? You can do everything in terms of X, Y, Z, and it's still, the identity doesn't change. Right, I get 2 of these guys, but I only want to spend time on one because we have another section to begin today. Any particular preference, 26 or 27? It's all about finding the equation of a tangent line, which I think we're pretty familiar with. But is there either one of these two you want to see what the derivative part would look like?
Probably 26 because I'm not a big fan of square roots.
Okay, sounds like a good plan. So there's the function. We're being asked to find the equation of the tangent line at 0.12. Whenever you see a square root, in fact, if I was doing this question, wouldn't I probably write that down, not this? So we got it as a half power. Can you identify the inside function? Anybody? In this question, what is the inside function?
The 3 plus x cubed.
Yeah, pretty easy to find, isn't it? If it's inside the brackets, or Americans call it parenthesis, but I'm going to call it brackets. I'm used to calling it that. It's this guy, right? So, derivative. Multiply by the power. Reduce the power by 1. Times the derivative of the inside function, which in this case is 3x squared. I'm now going to call this 3x squared. That half can be a 2 on the bottom, and that guy can be a positive a half power on the denominator. And then make it look like the original. Are we comfortable with the derivative? It wasn't the worst looking one in the world. Not too much in the way of style points. Now, we are interested in the slope of the tangent line at 1, 2. That means at the x coordinate of 1. So the slope of the tangent line is going to be the value of the derivative when x is 1. So it's going to be 3 times 1 squared over 2 times the square root of 3 plus 1 squared. Well, 1 squared is 1, 3 times 1 is 3. 3 plus 1 is 4, square root of 4 is 2, 2 times 2 is 4, so the slope is 3/4. And now I'm going to call this guy x1, y1, and we will use our standard, as we use pretty much every time, the point slope equation. And we are now going to be y take away 2 is 3/4 x take away 1. Distribute the 3/4. And then if you add 2 to both sides, now I know the answer to that, but let's pretend I didn't. You would go -3/4, add 2, and then you could do math button choice number 1 and turn it into 5/4. Just in case you're a bit rusty on your fractions. And that's the equation of a tangent line. Now, if I had time, when I plug this guy into Desmos, I would plot that point in Desmos, and then I would draw this in Desmos. And can we pretend that it looked like this? Wouldn't that be the check? Everybody was happy, we did it right. Any questions about chain rule before we move on to our next section? Any questions? Okay. You have got a lot of work in chain rules. It's not one of those things to be taken lightly. So put the effort in, and it will supply you with benefits. Excuse me, I've got sorts of notes mixed up here. This is the one I'm looking for. Our next section. It's called implicit differentiation. It's a niche market. You only use this method, and it is a method, a process. There are no formulas attached to it, but you only use it in implicit expressions, right? That's the only place it gets used. So that's what I mean by a niche market. So what does an implicit expression look like? Well, if you have an equation or a curve or an expression written where the x's and the y's, so it's always going to be x's and y's typically, are mixed up, or at least not written in the usual y equals f of x format, right? That's the normal way you write formulas, right? If it's jumbled up, it's implicit. Now, you might recognize this one. Isn't this a circle radius one? Right. So if I sketch this guy, it would look something like this. Which for me is not bad. Slightly egg looking, but not bad. Now, can you imagine a random point on that curve? Let's say that point there is P. Would you agree that there's a tangent line to that curve at P? And since there's a tangent line, and that means it's got a slope. And if it's got a slope, doesn't that mean it's got a derivative? So we should be able to find the derivative of an implicit expression, right? It has a tangent line, it must have a derivative. But the way that we get that is quite different from the normal product rule, quotient rule, chain rule, power rule thing, right? We don't quite do it that way. Now, you could say, well, I could rearrange this equation to be y equals, and then I could do it, and actually that would work, right? You'd have some problems, but it could work. If I tried to do it that way, I guess my approach might be to solve for y. And no, that is not 1 minus x. I also have the added problem that now I do have a plus minus problem, don't I? So can you see that it really doesn't lend itself? Plus, what do you do? What do you do when your implicit is even more jumbled up? Would you agree there's algebraically, it's an impossibility to write this thing as y equals, right? So that technique is out. We're going to have to look at it differently. Right? Now, some notation. When you write a function like this, you can tell me the derivative using that notation. You can also tell me the derivative using that notation. Now, we've not used dy by dx much. I don't like using it just because I'm lazy. Isn't it easier just to call it y dash? There's less things to write. But I could have done all the questions today and said dy by dx equals, and it would have been correct, because this and that are all the same thing. Aren't they all meaning the derivative of the function? So you're going to see me using that a lot today, not these. Still not quite there, because there's a few other things I have to tell you about. Suppose you take a function like x squared, and I said differentiate it. Would you all agree the answer's 2x? No biggie. If it was e to the x, would you all agree that the answer is e to the x? And one more. If I said it was sine x, then you would say the derivative was cosine x. To be able to do implicit differentiation, we have to figure out how to deal with the y's that are going to be there, right? Because there's going to be a y squared and a sine y and a e to the y and all sorts of other things with a y in it. And this is how you deal with it. If you have a y squared term, your answer to what is its derivative is 2y times dy by dx. Think of y as your inside function. Then y squared gets you 2y times the derivative of your inside function. If it was e to the y, its derivative would be e to the y times dy by dx. And if it was sine of y, you get cosine of y times dy by dx. Have you noticed that the only difference between differentiating x's and differentiating things that use y in terms of x is that you add on an extra dy by dx? Have you noticed that? That's the only difference. So we are now going to take all those bits and pieces and use it to solve finding derivatives of implicit expressions. So let's start with that one. Step one is differentiate. Well, let's see. Each term gets differentiated with respect to x. So x squared gives me 2x plus, if you differentiate y squared, you get 2y times dy by dx. And what do you think you should get if you differentiate 1? Big fat 0, yes. And then step 2, solve for dy by dx. And that, what I mean by that is rearrange this so it's dy by dx equals the expression. So as long as you do it to both sides, it's okay rule. So I'm going to subtract 2x from both sides. I'm then going to divide both sides by 2y. And step 3, style points. The good news is that most of the time, there isn't going to be that much in the way of style points. So the derivative of this implicit expression is that guy. Okay. Let's show you how you could use it. Okay, here's the unit circle. That's what x squared plus y squared equals 1 looks like. Let's take a point P that I happen to know is on it. root 2 over 2, root 2 over 2. Can you just trust me that that point is actually on the unit circle? I mean, if you get your own unit circle, you could check it, right? Now, what would be the slope of the tangent line at that point? Well, if you want to find the slope of a tangent line, you write it like this at the point, bit clunky, at that point there. So it's negative root 2 upon 2 over negative root 2 upon 2, which is actually negative 1. Does that seem reasonable looking at my picture? So we now have a way to find the derivative of implicit expressions. I don't want to call them implicit functions because technically they're not a function, because for a function, doesn't this break the 1x gives you 2 values of y rule, right? So I might call it an implicit curve, I might call it an implicit expression, but I really shouldn't call it an implicit function. Okay, it's a been lawyer-esque, but you know, that's why I'm not calling it that. Now, you can do all sorts of weird things. You know, when you do implicit functions, don't you sometimes get some really weird looking curves out of it, right? But the cool thing is that this technique will be able to find you the tangent line at any point on that curve. Pretty powerful, right? That it can actually, you can still use calculus to do that. So differentiate, solve for dy by dx, and style points. That's your 3 kinds. Step 3 is not going to be a biggie. For chain rules, wasn't it horrible? There were a lot of style points, a lot of algebra. You're not going to get an awful lot in step 3. You might get a little common factor thing cancelling here and there. You might get absolutely nothing, right? The answer you've got is as good as it's going to go. So far, so good? Any questions? Okay, so basically practice. We're trying to show you more and more unusual or more complicated versions of that same question. The first one I'm going to start off with is pretty straightforward. No, I've no idea what that is like, but you know, you can plug into Desmos and let Desmos figure it out for you if you want to see what it looks like. Let's differentiate it. So that's step 1. 2x. If you differentiate 4y cubed, what do you get? Well, 12y squared times dy by dx. So you're comfortable with that? If you differentiate 4y cubed, you get 12y squared dy by dx, and if you differentiate a number, you get 0. So step 2 is solve for dy by dx. So I've got 12y squared, that fella, subtract 2x from both sides, divide both sides by 12y squared. A little bit of cancelling, not really that much. We're done. You happy? Nothing too strenuous. Of course, that's a simple one. So let's add a situation you've not dealt with yet. Well, I'm going to do the 2 bits that are easy. You differentiate that guy, you get 5. You differentiate that guy, you get 0, right? I guess the equals should be that. I have an x times a y squared, and I need to differentiate it. What technique am I going to use? What rule?
Product.
Product. Yeah. So this is going to be my f, and this is going to be my g. So I'm going to have to do f dash g plus f of g dash. Are you comfortable about the product rule, right? 2 things multiplied is the product rule. It would be nice if it was an x times a sine x, right? You'd see a product rule right away. But it's an x times a y squared. It's still a product rule, right? It's 2 things multiplied. Now, if you differentiate this guy, you get 1. You leave that guy alone. You leave this guy alone, and you differentiate y squared. You get 2y times dy by dx plus a 5 equals 0. I'm just tidying this up on this line. You get that? You can then do subtract a y squared from both sides and subtract a 5. And then to finish, divide both sides by this fella. And in this case, there are no style points. I can't make that better. That's me finished. Are we good? Matthew, you're looking puzzled. Question?
Yes, I guess that just has to do with the style points, because I'm assuming once you get the product of x, y squared, then you would have to keep going and it'll end up, I was doing it without watching you, and I ended up getting 2y times y plus x, but I guess that's the weird way of going about it.
I'm not sure where the y plus x came from. Did you get this line here?
Yeah, I guess I'll still stuck on the product of x, y squared.
Okay, so I ain't got a big enough hand. The first function is x. So we'll call that f. Its derivative is 1. The second function is y squared. Its derivative is 2y dy by dx. That whole package, the whole 3 things, is the derivative. So f dashed 1, untouched g, y squared. Untouched f, that's x, y dashed, right? The g dashed, I should say, is the derivative.
Okay, I see where I was messing up. I was still treating y like it was just a regular x, so I didn't put the dy dx. I just put
Gotcha.
y.
Are we good with that, guys? Any other questions? Give me a few seconds, I'm just getting my... There we go. So. You'll hear me okay? Right, let's pick... Okay, let's jump right into the deep end. Here is question 2. You have an x to the 4, an x to the 9, a y to the 9, a y to the 5 equals 8. So you're really getting chucked into the deep end here, because I got this term here, the x to the 9, y to the 9 to deal with, right? And that is definitely going to be a product rule again. Would you agree? Make this f, make this g. And we've got 2 different locations that have y's in them, which we haven't dealt with yet. So let's take each one in turn. If you differentiate this guy, you get 4x cubed. If you differentiate this guy, you're really going to have to do a product rule on it. So do that as a placeholder. Now, if you differentiate y to the 5, you don't just get, you don't just get 5y to the 4, don't you also get a dy by dx? Right, so if you differentiate y to the 5, you get 5y to the 4 dy by dx, and if you differentiate 8, you got 0. So that guy's done, that guy's done, that guy's done. Still to work on this one. Okay, if you differentiate f, you get 9x to the 8, and you leave the second guy alone. Plus, you leave the first guy alone, which is x to the 9, and you differentiate this guy, you'll get 9y to the 9. Did I go and do that again? 9y to the 8 dy by dx, plus this guy who's still there, and the whole thing is still going to equal to 0. Now, the next line is really cosmetic, but that makes me, I like it better. I mean, it totally is cosmetic. All I've done is change one term, and all I did with that one term is just rewrite its order a little bit. Right, we're all comfortable with that line. Right, this guy, all I did is rearrange this so it looked a little bit prettier. You know, number should go first, that's not a major issue. And then this guy, and it's there. Now, the goal for step 2 is to solve for dy by dx. And this is the first time that there are 2 terms that contain a dy by dx. So the first thing I'm going to do is nothing to those 2 terms. I'm just going to leave them on the left-hand side, totally untouched. Not going to do anything to them yet. But I am going to subtract 4x cubed from both sides, and I am going to subtract that guy from both sides. Are you comfortable with why I'm doing this? Remember, the goal is to get dy by dx.
Professor.
Yes,
9x to the 8. You have 9x squared.
thank you. Right, where are we going now? Look at the left-hand side. What do you think I should do next?
I'll remove the 9x to the power 9, y to the power 8 plus 5y to the power 4 from the dy over dx.
Okay, essentially what you said, just paraphrasing it, is I'm going to pull it out as a common factor.
No divide by.
And yeah, are you all comfortable that common factors are just things that are common to both factors, right? Both terms, right? And dy by dx is a common factor, just like x cubed could be. But I only pull out this guy. Even if there is a y to the 4 or something else going on, don't do it. Only pull out the dy by dx's. It just makes your life easier right now to do it that way. And someone said, divide. And so I am going to do that. I'm going to take this ugly answer and divide it by that ugly answer. So far, so good. Now, style points. Pretty much, isn't style points going to be just factor the heck out of everything now? So it's at this point here that I start looking to see if there are any common factors. And if I look at the top, I can pull out an x cubed. And if I look at the bottom, I believe I can pull out a y to the 4. But apart from doing that, would you agree nothing cancels? So that's the best I can do. Sometimes you'll do it in an x cubed and an x to the 6, and you can get some cancelling. But we're finished. Not too much in the way of style points at all. Any questions? Have you noticed that this is pure method, right? There isn't a formula that's being used, right? Except, you know, things like the product rule as part of the way that we approach this. So let's try this version. This guy equals that guy. So I'm going to differentiate. Are you comfortable that this is a product rule on the left-hand side? So I'm going to be doing an f dash g plus f of g dashed. And the derivative of this guy is 1. Take away, oh, okay. What is the derivative of y with respect to x? What do you get if you differentiate y? It's a bit sneaky, this one, actually.
Just dy dx.
Yeah. Technically 1 times dy by dx, but we just write dy by dx. Are you comfortable with that? Anytime you differentiate a y, even if it's just a y, you always finish with times dy by dx. So you differentiate y, you get 1 times dy by dx. Now, product rule. Differentiate that guy, you get 1. Leave this guy alone. Leave that guy alone and differentiate e to the y. And that gets you e to the y times dy by dx again, right? If you differentiate anything with a y, finish with dy by dx. Are we comfortable with that? Right. Now, step 1's finished. Step 2, solve for dy by dx. So as long as you do it to both sides, it's okay, roll, right? That's my name for what we're doing here. And any suggestions for what I could do to both sides that would get me closer to finding dy by dx? Here are 4 terms. What could I do to both sides to get closer to my goal? What could I do?
Add
Could
dy
you
dx
add
both sides.
dy dx to both sides and then make it a common factor?
You are ahead of the game, and yes. What should I do about this e to the y? Because 1 times e to the y is just e to the y. What should I do about that guy? Should I leave him here or do something about him? This guy here. What should I do with him?
Just
Oh, right.
subtract him from the other side?
Okay, so subtract e to the y from both sides, add a dy by dx from both sides. Isn't that the classic solve equation method, right? Adding and subtracting things. Now, you already mentioned the next step, so I'll just put this in. Can't we pull out a dy by dx and only a dy by dx as a common factor? One last line. What do I do to both sides then to find dy by dx?
Divide x e to the y plus 1 to both sides?
We are finished. There is a kind of flow to this. You begin to see it, right? You differentiate. You're probably going to get 2, sometimes 3 dy by dx's. So you're going to have to do this, rearrange the terms, add things, subtract things from both sides. Eventually, you'll get something that looks like this. Then you pull out a dy by dx, and then you finish with the divide. Very, very similar algebra in many cases. Oh, let's do a trig one. What trig one should I do? Oh, let's do 2 trig ones. Question 4 is the easier trig one. This guy. Now this is the easier one, so wait till you see the next one. Now I'm going to differentiate a sine. I get a cosine. Oh no, by the way, that's the y. Misshowed. If you differentiate a cosine, you get negative sine y times dy by dx, right? It's got a y in it, it's going to be that. If you differentiate x squared, you get 2x. But if you differentiate y squared, you get 2y dy by dx. The most common mistake people make is that they forget for things like y squared, they just write the answer 2y. They forget about the dy by dx. Or for the cosine y, they just write minus sine y and they forget about the dy by dx. So you have to be aware to be careful about the dy by dx's, right? If you differentiate anything that has a y in it, make sure that you finish with dy by dx. Now in this particular one, I am going to subtract 2y dy by dx from both sides. And I'm going to subtract a cosine x from both sides. I'm then going to pull out dy by dx as a common factor. And then, pretty typically, I'll finish by dividing. Not too bad, really. Differentiate. Solve for dy by dx.
So is using the Leibniz notation the only way to do this?
You can use the y dash notation if you want to. The problem I have with y dash, and this is me personally, when I use y dashes, they start looking very like y to the power of ones, and then next line or 2 lines later, I then add them together and call it 3y cubed or something stupid like that, because that's what I do. Can you see that the dash notation doesn't play well with this process? I think dy by dx makes it different enough that I'm not going to do that. So yes, technically you can do y dashed if you don't like dy by dx, but my own personal preference is that I make too many mistakes because I'm careless. So I just get into the habit of always doing that, and I found that I don't make that kind of mistake anymore. Would you agree it would be very unlikely, even for me, to turn that into 3y cubed? But on a bad day, couldn't I turn that into 3y cubed if I wasn't careful? Do you see why the notation causes trouble? For me. You can choose whatever you want to do. Now I promised you that one was bad, but wait till you see this one. This one is horrible. And it's horrible for one very simple mistake, because it's the first time we've seen it. Technically, there's a chain rule in this question, and it isn't even obviously there, but it is a chain rule. So let's do the easy ones. Differentiate a sine, you get a cosine. Differentiate a sine of y, you also get a cosine of y, but don't you get a dy by dx to finish? Are we getting to the point where that's second nature and you don't have a problem anymore, right? This is a sneaky one. This is the one that will catch you, if it catches you at all. Well, I want to differentiate the cosine of x plus y. Well, I know the answer to that is negative the sine of x plus y. So what are you talking about? There's no problem. I'm done. No, you're not done. This is the cosine of somebody. This is x plus y is my inside function. So if I differentiate the cosine of x plus y, I do get the negative of the sine x plus y, but shouldn't I also get the derivative of the inside function? You weren't expecting that, were you? Agreed? It is technically, right, a chain rule. So you differentiate it times the derivative of the inside function, and the derivative of x plus y is that guy. So what I'm going to do next is basically distribute. So that's negative the sine of x plus y, negative the sine of x plus y dy by dx. So I'm basically distributing that. It's going to be a cosine of x plus the cosine of y dy by dx. Right, that's all the hard stuff over. Now it's pretty much like every question we've done. Don't I want all the dy by dx's over here, and don't I want the stuff that doesn't have a dy by dx over here? So I'm going to add sine x plus y to both sides. And I'm going to subtract the cosine of y dy by dx from both sides. And if you can get to there, the next two lines are pretty much standard, aren't they? They all kind of look the same. I'm going to pull out a dy by dx as a common factor. And then divide both sides by that guy. And there's nothing worthwhile to do to that, so we're finished. There is no style points. Okay, a little quick pause for a minute. Are we good? Any questions? Have you noticed up to this point, we've only been doing product rules and one chain rule, and quite a hidden chain rule. You know, there's one exception. I haven't done a fraction yet, right? I have not done a question with a fraction in it. So let's do one with a fraction in it. Agree, left-hand side is definitely a fraction. Now, if I wanted to do this question, couldn't I call the top f and the bottom g, and wouldn't I then use the quotient rule? Can you see how ugly that's going to be? Can you just imagine how ugly? Wouldn't it be nice if we could avoid that? So I'm going to now bring in my just because you can doesn't mean you should rule. I haven't used that much. What that means when I say that is just because it is possible to do this question as a quotient rule doesn't mean I have to do it as a quotient. I'm going to do that. That's a clue to what's going to happen next. I'm not going to differentiate. Algebraically, what am I going to do next?
Multiply both sides by x plus y.
Right, or as some people call it, cross multiplication, right? So it's going to be x plus y times y squared plus 3 equals x squared. What do you think algebraically I'm going to do next? What am I going to do with this?
Foil it.
So I'm going to have an x y squared plus a 3x plus a y cubed plus a 3y equals x squared. Now, that was the guy we started with. Mathematically, isn't this equivalent to it? Because I've not changed what it's equal to. Haven't I just changed the way it looks? Would you agree that that is much easier to differentiate than this guy? Right? Product rule, 3x, 3y squared dy by dx, 3 dy by dx is equals 2x, right? You agree it's not the worst looking question in the world, right? If you try to do this one, wouldn't you have to do f dash g minus f of g dash all over g squared equals 2y dy by dx plus 0, right? Trust me, it wouldn't be pretty. I'm not saying you couldn't do it. And here's a rather interesting idiosyncrasy. If you did this one and you found dy by dx, and you did this one and you found dy by dx, they wouldn't necessarily look the same, even although they are identical. Right? In other words, it's the same answer. Might seem weird, but that is the case. So don't worry about that. If you use the quotient rule, you get one answer. If you used what I've done here, you should get a second answer. They are both correct. Which one did they do? Right. Well, to show you the one that they did, that's the answer that they've given. Now, I don't know, let's see what their working is. Oh, they did it as a quotient rule, and that's what the eventual answer ends up being. And if you did it this way, you could end up with a different looking answer. Are we good with that? So, moral of this story is, if you see a fraction, right, get rid of it, right? Do a cross multiply, make it go away. If you can't make it go away for whatever reason, then use a quotient rule. But I would avoid using the quotient rule whenever possible. It's just really ugly and not easy to keep track of terms. So let's look at 9.
So even when we have trig functions as a quotient, can we still cross multiply?
Oh God, yes, please. Yeah, trig function. If that one I just talked about is bad, trig function are even worse when they're fractions. I mean, they are the identities that could be hidden inside one of them would make your hair fall out. So at least try and avoid it. I mean, there are going to be questions, I guess. I can't see any, thank goodness, but theoretically, there might be situations where you just can't avoid it, right? Then use a quotient rule, right? If you can't avoid it, you just got to do it. But hopefully, you won't see that too often.
How do we know if it's
If you-
unavoidable or not?
If you can set up a cross multiply, right? So an unavoidable one would be something like this. But you could either, there's not a cross multiply in the world that's going to save you, right? On the other hand, can you do a cross multiply on that one? So we're not going to get into questions because it's just not reasonable that are so ugly that you take 2 days to do, right? I could write down the most ugliest looking expression in the world, and theoretically you could do it as implicit differentiation, but nobody would expect that type of question. So within the realms of possibilities, the fractions are not going to be your biggest worry, right?
Okay, I just wanted to make sure if my go-to is to cross multiply, it's like, no, I'm not going to get every single one wrong.
Yeah, your cross multiplying is going to be totally fine. So question 9 is, here is an implicit curve, and we are going to find the equation of the tangent line, which is a pretty common question, agreed? Find the equation of the tangent line is one of those things that you get to do quite a few times. Finding the derivative, of course, is a lot more work. Would you agree? Product rule and product rule. So I'm going to call this F, going to call this G, going to call this guy F, going to call this guy G. So we've got a lot of product rules going on here. F dash G plus F of G dash for this fella, and F dash G plus F of G dashed for this fella. Now, if you differentiate Y, you get 1 dy by dx. You leave the second function alone. First function left alone. If you differentiate e to the sine x, you do get e to the sine x. Is that all you get when you differentiate e to the sine x? Correct. You agree that's a chain rule. So differentiate the inside function, you get another cosine, and that's that done. This fella is 1, leave the second guy alone, plus leave him alone, and if you differentiate a cosine, you get a negative sine y followed by a dy by dx. Are we comfortable with the differentiation part, right? Now, that guy has a dy by dx in it. This guy has a dy by dx in it. This guy doesn't. This guy doesn't. So we're really like shuffling the cards, right? I'm moving the dy by dx's over here. I'm moving the things that don't have it over here. And so I'm going to essentially add that to both sides. So what have I got? I've got a dy by dx, e to the sine x. And I'm going to add an x sine y dy by dx. And then I've got 1 cosine y. And I'm going to get rid of this guy by subtracting them from both sides. Then I'm going to pull out a dy by dx as a common factor. And then divide both sides. And I've gone in. There we go. Just pausing for a minute. I think it's pretty obvious that you're not going to make that pretty, so I'm not too worried. So let's get the slope of the tangent line. Well, it's going to be the value of the derivative at the point 0, 0. So that's going to be the cosine of 0, take away 0 times e to the power of sine 0 times the cosine of 0. And then it's going to be e to the power of sine 0 plus 0 times the sine of 0. Okay, 0 times everything is 0, so that's just nothing. And the cosine of 0 is 1. 1 take away nothing gets you 1. E to the sine 0 is e to the power of 0, and e to the power of 0 is 1. And this guy's nothing. 1 plus nothing gets you 1. After all that hard work, isn't the slope 1? Now, to save some time, I'm not going to finish this off, but would you agree you've got a point, you've got a slope. It shouldn't amaze you that the answer is y equals x, right? You know, it passes through the origin, got a slope of 1. But you could use a point slope equation if you wish. Next one, yeah, we've got time, is a trig one. And we're interested essentially what's happening at that point. Now, if you differentiate a tangent, what's the derivative of a tangent? One of our 6 trig ratios, what's the derivative of a tangent? Secant squared? I think that's what I saw mouthing. Correct. Secant squared of x plus y. Uh-oh. It's a chain rule. Times the derivative of x plus y, right? It's not just the tan of x, it's not just the tan of y, it's the tan of x plus y, right? It's a chain rule. So differentiate it, you get this, times the derivative of the inside function, which is 1 plus 2y by dx. If you do a secant, you'll get a secant tan. But isn't this also a chain rule? Right, x minus y is our inside function. So we finish with the derivative of the inside function. And the whole thing's equal to 0 because that's the derivative of 2. Now I'm going to distribute that and distribute this, and oh god, it's going to be ridiculous. I'm going to get that guy plus that guy times dy by dx. And I've got this guy times 1. So I'm going to get secant tan. And this guy times all of that. Not enough room. Take away a secant tan dy by dx. And that's going to equal 0. Right, so I have this guy as a dy by dx attached to it, and so does this guy. So I'm going to leave them exactly where they are. So I'm going to have a secant squared x plus y dy by dx, take away all this, equals, subtract that from both sides and subtract that from both sides. If you pull this out as a common factor and divide, to save some time, can you just trust me that you end up with this ridiculous looking fraction? All of this stuff. Divided by these two guys. You can fill in the details later. So I can now find the derivative at that point. Right, so it's going to be negative secant squared. Pi upon 8 plus pi upon 8 gets you pi upon 4. Take away the secant in nothing times the tan in nothing is just nothing. So I'm not even going to write down the calculation. Now this guy is going to be secant squared of pi upon 4. Take away some more nothings. And it doesn't take much. Would you agree that that ends up being negative 1? Can you see it? And then point slope equation and do your thing. And according to what I have in front of me, which seems reasonable, you could get that. Oh, that was a bit quick at the end. We're pretty close to finishing this one. We'll look at some other things that we haven't dealt with tomorrow, but last name and bye-bye for now. I will hang about if there are any questions at the end.
Professor.
Yes, Matthew.
I was just
Hold on a second, Matthew. I'm getting weird issues with my earphones, so I couldn't really hear you easily. It was some kind of garbled sound. So what you were saying, Matthew?
Can you hear me now?
Yes, sort of. It might be your side then. But keep talking. I can hear when you said, can you hear me now?
Yes. Should we explain to me the derivative of y is first it's 2y. Y
Okay,
squared is
hold on. Sorry,
times-
Matthew. Hold on. Coral, can you hear what Matthew is saying? Okay, it's your problem, Matthew. It's not my side then. That's a pain in the butt. I don't know how you can make your mic work better. Is there something you can do?
Is that better?
Yes, it's a lot better.
Okay.
I don't know what you're doing, but keep doing it. Right.
My question is, can you re-explain to me why the derivative of y is dy over dx?
Yes. Okay. So if I asked you for the derivative of y cubed, you would say it was 3y squared times dy by dx. You're comfortable with that, right? Yeah. And now if I go down 1 power to y squared, you would tell me it was 2y by dx. Again, you're comfortable with that. Now, if you do y, it's 1 times dy by dx, which is just dy by dx.
I guess my
Yeah.
question, is the dy over dx just you saying the derivative or?
Yes, it is. That's what I'm saying.
Okay.
That just is another notation, if you want to know, it's called Leibniz's notation, as Keith was saying, for the derivative. I prefer that notation rather than the y dash notation or something else. It just looks nicer. I was going to say, if I said to you, differentiate this guy, you'd get x squared, and if I said do this one, you get 2x. But if I said x, wouldn't you get 1? You see the comparison is very similar.
I guess I'm wondering, why do you have to include dy over dx for y and not for x?
Well, technically speaking, if you want to use Leibniz notation, if I differentiate x, I'm basically doing dx by dx, which is 1. If I'm doing y, I'm doing dy by dx, which is not the same thing. I mean, that's maybe not a good explanation, but that's the reasoning behind this notation. Leibniz notation is that if you differentiate x with respect to x, you just get 1, because that's basically just 1. If you don't like that, how about the answer is 1 dx by dx? Now, can you see why that becomes 3x squared, why that becomes 2x squared, and why that is 1? We wouldn't normally write that, but technically that's what's happening.
Okay.
Does that help?
No, that helps.
Right. And the best rule to just remember, like do as I say kind of thing, is if you see a y and you're differentiating it, don't you finish with dy by dx.
Yeah, that seems like what I'm gonna have to do.
Right, just say to yourself, if I'm differentiating it and there's a y in it, the answer finishes with dy by dx. Right,
Okay.
Cora, what's your question?
I just stuck around in case someone asked a question I didn't think of.
Did you like the explanation, or if it confused you, ignore the last 5 minutes, because sometimes things become less clear after an explanation than they do before it.
No, I liked that. It became more clear. When you are, because when I look at like calculus online, they keep the dy dx through like everything, or instead of like writing f dashed y or f dashed of x.
Oh, every situation, they just use the dy by dx notation.
If we do calculus in the future, are professors going to ask for it written differently, or is this pretty standard?
Pretty standard. I mean, the 3 main ways that derivatives are written is y dashed, f dashed of x, or dy by dx. That's it. It depends on what the question's written like. If someone says to me, that guy, then f dashed x is the way to go, right? That's pretty standard. Everybody's going to do that. The change might happen when it's written like that, because you might get, and there's nothing wrong with it, that notation, or you might get that notation, right? And what you're telling me is that you're saying almost always this notation, but I bet you they almost always have y equals as the way the question was started, right? Now, if the question had started like that, they would have written it like that. So I can't give you a good reason, except maybe they're just being consistent, right?